Well, you guys, it's open to a coconut.
So as part of the exam review, we're going to take a look at the problems. The first problem that you had was the earliest start, earliest finish, latest start, latest finish, and calculating slack. Most of you did pretty well with that. There were a couple of bumps maybe on the latest start, latest finish, but again, you needed to identify the critical path, which again is the longest path through the diagram, right? You needed to draw the precedence diagram. It should have looked like this, okay? And then earliest start, earliest finish, latest start, latest finish, based on how we set up our T-tables and walk through that. And your slack time is latest finish minus earliest finish, or latest start minus earliest start, okay? And again, most people did relatively well on that one. Okay. Then the next, are there any questions about that one before I go on to the next one? Okay. All right. So the next one was about, you've got a project and we're going to use the critical path method, and we're going to find activity times. And in order to do that, you needed to use the formula to find the times to put onto the diagram. You needed to do A plus 4M plus B divided by 6 to get the estimated time, and then you needed to apply that to the diagram that you drew, your precedence diagram, to find the critical path. And the critical path should have been B, C, E, G, H, right? Because I'm going to add up all of the times that we calculated, okay? And then you're asked to calculate what are the variances associated with each task, okay? And variance is calculated by B minus A divided by 6 squared, okay? And they should have been, A should be 0.69, B 0.11, C 2.25, D 3.36, E 0.11, F 0.44, 2.77, and 2.25. Okay? And then you're asked to, what's the Z-score that we would use to identify the probability of completing the project? And in order to do that, you need to know that the Z-score formula was the desired completion time minus the estimated completion time, right? And the desired completion time comes from the problem of 18 days, and you calculated the expected completion time at 17.67 days. And then you're going to divide that by the sum of the squared variances that are on the critical path, right? So then you're going to come back to the critical path and pick those variances off and take the square root of those, okay? All right, and so at the end of the day, you should have had a 0.12 there. Yes? Mm-hmm.
You gave me credit for that one because I tried, but I didn't give any credit for that because I got it wrong.
No, I think that I couldn't see where you were, I didn't pick out where you were calculating that as I went through. So that's just, I missed that. Go ahead and circle that and I'll come back to it. Okay. Any questions about that one before we move on? Nope. All right. And then the next one is where we were going to work with schedule variances, budgeted cost of work scheduled, budgeted cost of work performed. Okay. So in order to crunch the numbers on this one, I find it easiest to set up the table of actual work completed for each activity, budgeted work completed, then identifying the budgeted cost and the actual cost, right? And so here's the information that we have from the problem. And then for the schedule variance, I need to calculate budgeted cost of work performed. So it's going to be, I'm going to take what was the budget, or excuse me, budgeted cost of work performed comes from our actual percentages that we've completed, 100%, 50%, and 25% of the budgeted cost, so of 1.5, 3,000,000, and 600,000, and then I sum those up to get my 3,150,000 for budgeted cost of work performed. Budgeted cost of work scheduled, right, comes from what did we say we were going to complete, those percentages, times those budgeted costs, and that gives us 3,030,000. Okay, and so my schedule variance is those two subtracted from each other for 120,000. Okay, and then my schedule performance index becomes, again, that you probably had it on your formula sheet, budgeted cost of work performed divided by budgeted cost of work scheduled, right? 1.04. Cost performance index, budgeted cost of work performed divided by actual, so 3.1 or 3,150,000 divided by 3,125,000. So in both cases, when our index is greater than 1, it says that we are ahead of the project expectations. Okay? Any questions about that one? All right. All right, so this one we were to determine the critical path. You're given the diagram, right? You guys should be pros at that by now. So then the earliest completion time comes from the critical path for 34, right? But in order to determine which activity you're going to shorten, right, by crashing the project, you have to set up what's the cost per day to crash, okay? And so in this case, we have to identify the cost of crashing, which is the total cost minus the normal cost. 8,100 minus 7,100 is 1,000, and we can only do 1 day, right? Normal time minus crash time is 1 day, okay? So that's $1,000 per day, okay? If I'm going to crash this activity B, 7,100 minus 5,000 is $2,100, right? And again, there's only 1 day difference between the normal time and the crash time. So you have to keep working through. This is normal time minus crash time in the time column, and your cost is going to be your crash cost minus your normal cost, and then you divide your cost by your time to get the cost per day. What you're looking for then is the lowest cost in terms of which 3 projects or which 3 tasks are you going to shorten, the lowest cost, right, that's on the critical path. Okay, so I have to come back to the critical path and look at A, C, D, F, G, right? And if I look at A, C, D, F, G, and I just asterisk those, so that helps me see that a little clearer. A is clearly the lowest cost, and that's only 1 day, right? And so then I have to look for the next lowest cost, C at 1,050, D at 1,500, F at 1,550, or G at 2,800. So it's C, and there are 2 available days there, so it's A, C, and C. Okay. And then in order to get my total cost, I take the normal cost of the project and add in the cost of crashing those 3 tasks to 38,300. Any questions on that? Okay. All right, so what's the theoretical flow time of this process, right? We would take the flow time across the 2 paths and identify the one that's the longest, and that would be the theoretical flow time, right? So I'm thinking that's 25 and 20 is 45, 55, 60, and 30 is 90. So it's this path across the top. Okay. What's the capacity of the process per minute? If you remember, we said you need to find the bottleneck of because that's the fastest that it's going to flow off of. If you think of this as a production line, well, the bottleneck is the longest task here at 30 minutes. Okay. And so it's 1 product for every 30 minutes, or 0.03 products per minute. And then the question is, if I add another person on the inspection workstation, so if the inspection workstation is here, right, at this workstation to 15 minutes, what's the theoretical flow time of this process? Well, then I'm able to take 15 minutes off of that flow time, so it's 90 minus 15, which is 75. Okay? Any questions on that one? Kind of a questionless group this morning. All right, and the last one, a manufacturing company has a sub-process consisting of 2 steps. The first step is to dip the part in insecticide. The dipping process takes 20 seconds. The second step is the drying process, and it takes 90 seconds. So, just a quick draw says I'm going to dip it 20 seconds, dry it for 90 seconds, so my total flow time is 110 seconds. Now assume that 40% of the dipped parts that is identified before the drying step, there's a quality issue, and they must be run through the dipping operation a second time. So what's our revised flow time? I take 20 times 1.4, or 140%, to give me a 28-second revised activity time for the dipping process, and add it to the 90 seconds for 118 seconds. Okay? All right. I will do a quick check here. It's taken me I had intended to have this ready for you this morning. I've been on the phone with Jackson quite a bit to get this squared away. So sorry that you're having to wait for me to look it up, but I'll tell you kind of the overall how folks did kind of thing. have to find the exam on here. That's the disadvantage of having so many. Okay, here we are. All right, so there are 250 points possible. So 10% of that would be 225. So it looks to me like we have 3 A's, right? And then 3 B's, and then a C, and then, let's see. And then roughly 2 Ds then. So kind of a pretty good distribution across the grades there. For those of you that didn't do as well, I'll just encourage you to do the practice problems next time. I think that would have made a difference. And I think using Quizlet to prep for the terminology. And on the multiple choice, is that kind of what most of you found, is the Quizlet was the most helpful for that? So make sure that you're using those resources as you're prepping for the next exam. Okay? All right, any questions? Nope? Okay, so I have an adjustment to do there. Okay. Thanks.
Strawberries for good.
All right, well, let me go get Hunter before we get started. I should not show him the problem, right? Because I think that would make all the difference in his grade. What do you think?
I know. You take what you can get.
All right.
I know the feeling. My parents didn't.
And it has sugar on it, so my family doesn't eat it.
It eats sugar.
But they don't eat carbs.
All right, so we're going to move into part 3 of chapter 3. And I broke the chapter up into this way so that you can kind of keep distinct in your mind that we have linear processes. We can work on those on financial flows, right? And we can turn around and we can do Little's Law in nonlinear processes. So today is going to be about nonlinear processes. And if you can kind of, again, when you're looking at it, you're going to be able to see, based on what we did on Tuesday, how you can handle the linear process, and then today, how do we handle the nonlinear process. Okay? All right. So we're going to jump right into it. So until last year, we're going to use this example. AUTO-MOTO, what we'll call Process 1, Financial Services, process each type of application individually. Okay, so they're a loan processing company, and they get on average 1,000 loan applications per month. So loan applications per month makes it what? I'm going to start with Emily since you're looking at me. Throughput, inventory, or flow time?
Throughput.
There you go. Loan applications per month. Okay, and so we're going to assume that there's 30 working days in a month. 20% of those loan applications are approved, 80% are rejected, and there are 500 applications in the process on average. Scotty, what does 500 applications represent?
Isn't that inventory?
It's inventory, right? So we have inventory and we have throughput, okay, telling us that we should be able to calculate flow time, okay? So here's a drawing of that process with the chart that I like to create, right? We have 1,000 apps per month going on the arrow going in for our throughput. Inside that process, we have 20% that are approved and 80% that are rejected, meaning that exiting the process, we have 200 approved and 800 rejected, okay? And it is a stable process because you have 1,000 apps per month going in and a total of 1,000 apps per month coming out. Now, they can be on different paths as they exit, right? But it's still a total of 1,000 applications per month, okay? And so kind of the next thing that we want to do is I think that a lot of times talking in terms of a percentage of a month is not as useful. So a lot of times we go ahead and convert to days, and you can kind of tell that's where they're leading us because they tell us that we have 30 days per month, okay? I'm going to try to write on this, okay? And so that being said, I'm going to convert 1,000 applications per month, right, into how many applications per day. by taking my 1,000 apps per month and basically multiplying that by 1 month for 30 days. Or the same thing as dividing it by 30 days. And so then that's going to equal 33.33 apps per day. And if you're having trouble reading my writing as I use the pointer, know that this information is on the notes too, so you can go back and grab it from those notes if you need to. So now I can determine how many days it takes on average to complete this process, because flow time is equal to inventory of 500, right, applications, divided by throughput, which is 33.33 applications per day. And so what happens is I cancel out my applications, right? And I finish it out. It's 500 divided by 33.33, right? That tells me that's on average 15 days. So in process 1, where I just have all of the applications come in and go through the same activity step, it takes me 15 days, okay? But one of the things that they're interested in is maybe there's a way to do some suggested improvements, okay? And those improvements are that maybe they have an initial review team set up to pre-process the applications according to strict but fairly mechanical guidelines. Okay, I would guess that Hunter, when you guys and Kaylin and Courtney, when you guys are working on your project, you might find some of this kind of thing that applies, right? Sometimes things take time at a particular step because we route it through the same person, right? But they're making kind of what I would call decisions that are based on this mechanical set of rules. So if you just communicate the rules to someone, they can make the decision and it never has to sit and wait, right? I see a lot of that in the HR processes that we use when we do stuff around campus, right? Everything has to go to the provost and the president's office for final approval, but they've already approved it twice before that, right? And so in my mind, the only reason they would disapprove something is if there's a significant change, right? And so if you can look at it and say there's no significant change, you can move it through the process that much quicker. Okay, so that's what they're suggesting here, is you can look at an application early on and decide, is it an easy one or is it a challenging one? So each application falls into one of 3 categories. It looks excellent, needs more detailed evaluation, or we can just reject it because we know it's not going to make it through the process. So A and B applications would be forwarded to different specialist groups, and each subgroup would then evaluate the applications in its domain and make those accept and reject decisions. Okay, and so with that being said, now we get this process, so you can see it's no longer a linear process, right? Every application doesn't go through every step in the process, so it's what we call a nonlinear process, right? We have 1,000 applications per month that go through the initial review. We have 25% of those that go through the excellent review. So what's 25% of 1,000, Hunter?
250.
250. So that means that we have 250, right, that go through the excellent review, okay? Kaylin, how many go through the detailed review? Another 25%?
Oh, 25. Sorry, so 250.
So another 250. Okay, by the process of elimination or by calculation, 50% of them are rejected outright. So Courtney, how many are rejected?
Out of that 1,000?
Yeah. 500, right? And so then what you'll see is that these 3, right, sum back to the 1,000, right? And again, so we have this partial throughput. We parse it out going through these different steps, okay? So again, I want to do this for, convert it to days. We know 1,000 divided by 30 is 33.33. 250 divided by 30 is 8.3. Okay, and still 8.3. And 500 divided by 30 should be, I'm thinking, 16.7. Okay, so I have my throughput, right? So there are still 1,000 applications per month, and they all go through that initial review process. However, after they complete the initial review, 25% go through excellent, 25% go through detailed, and 50% are rejected outright. So now we know throughput at each activity. The problem then tells us that we have 200 in inventory at the initial review. So I know that I've got 200 in inventory here. So again, at a snapshot in time, we've just looked and said, well, how many do we have here? Okay, and I have 25 with the excellent review, right? And I have 150 with the detailed review. Okay, and I have 0 then with the reject outright, right? After they go through the initial review, they're out of the system entirely. So I would have 0 inventory there. Okay, so how do I tell how much inventory is in the system as a whole? Okay, well, I can still sum up across those locations. In a nonlinear process, you can still sum inventory. And I can say, because again, think about why that works, okay? Because it's a snapshot in time, right? And so because it's a snapshot in time, I'm just taking a picture of how much inventory is in the system at a particular time. So I can still sum inventory. So I have 375 units in the entire system. Okay, all right, if I think about my throughput for the entire system, is my throughput for the entire system 1,000 apps per month, or 1,000 plus 250 plus 250 plus 500?
1,000.
It is 1,000, right? It stays consistent. So for the entire system, my throughput is 1,000 apps per month, or 33.33 apps per day. Okay, so again, now I have 2 out of 3 pieces of information for Little's Law, and I can come back and I can calculate flow time. Okay, so so I can come back to this and I can say that inventory divided by throughput, 200 divided by 33.33, 1.575. Okay. Then I can say inventory divided by throughput, 25 divided by 8.3 is 0.675. 150 divided by 8.3 is 0.6. Okay. And rejected outright, 0 divided by 16.7. Sorry. I got to looking at the next slide thinking that was going to give me my answers. Let's double check this. 200 divided by 33.33 is, sorry, we're just going to make a mess here. I'm going to go not that, and not that. So 200 divided by 33.33 should be 6.0. Okay. The excellent review, 25 divided by 8.3 is 3.01. Okay. And the detailed review, which is 150 divided by 8.3, is 18.1. Okay, and then the rejected review is 0. Okay, so my question is, if I want to take the average time that it takes a unit to go through the inventory, can I sum up the time? I can't, because not every unit goes through every step. Okay, so what I could do is I could take a weighted average, right? I could say, well, I can look at those steps and see, roughly I can do the weighted average, or I can take the shortcut, and I'll show you the shortcut, and then I'll show you the weighted average so you can see that the two are the same. And because I have 2 out of the 3 pieces of information on the totals, right, I can take 375 and divide it by 33.33, and that's going to give me, right, the average flow time. And so 375 divided by 375 divided by 33.3 is 11.25. Okay, and again, that's probably the key point that you need to take away from this lecture. Okay, the key point is that you can sum your inventory, right, but you can't sum your flow time. Okay, and so if you're doing flow time for the entire system, and you have average inventory for the entire system, and you have average throughput for the entire system, or if you have throughput for the entire system, you can calculate it, right? But you can't sum it, because if you sum 6 and 3 and 18, right, that's going to be much higher than 11.25. And it's because only a certain portion of those units go through each step of the process, okay? All right, so let's look at if we were going to do it the long way. If we were going to do it the long way, we would look at it and we would say, well, for flow time excellent, we have accepted, they go through the initial review and the excellent review, right? So that's 6 days for the initial review and 3 days for the excellent review for a total of 9 days, okay? All right, and so we're just doing that on each of these steps. Flow time excellent rejected is still 6 days in the initial review and 3 days in the excellent review for a total of 9 days. Flow time for the detailed review accepted, initial review is 6 days, right? And the detailed review is 18, so it's 24 days. Flow time detailed review rejected, again, 6 days plus 18 is 24. And flow time for initial reject is only 6 days because it only goes through that initial review step. So we have the days in each category. We have the applications through each process. And when I'm going to do a weighted average, 175 out of 1,000 is 0.175, right? 75 out of 1,000 is 0.075. So I'm coming up with these weights to apply to the times so I can get the weighted average of the time that a unit takes to go through the process. Okay. What you can see is I can use that weighted average. So I take 9 times 0.175. That gives me my weighted days of 1.575. And are you following what I'm doing? I need some confirmation that you're following what I'm doing. Because I can spend a lot more time explaining it, but if you're getting it, we can just go to, then I sum those up and it's 11.25, right? Which is exactly what we did when we calculated it using the average inventory of the entire system divided by the throughput of the entire system, okay? So you just have to know in your mind that you cannot sum up the flow times, okay, if you have a nonlinear process, okay? If you are looking for the time in the entire system, then you're going to be using your Little's Law of inventory divided by throughput. If you're only looking at certain segments of the system, you may need to use the weighted average to figure it out, okay? All right, so then the question is, but what if we want to know the average time for accepted or rejected applications? Okay, well, this is what we had before, but the accepted applications are in green and the rejected applications are in yellow. Okay, and so we're going to go ahead and move on to the next slide, right? And so if I want, so this is the slide that we were looking at before. If I want to look at accepted orders only, right, I can do, again, the weighted average of how long does it take for these orders to go through, okay? And basically, we run that same process where we say 175 divided by 200 is 87.5% of the orders. 25 divided by 200 is 12.5% of the orders. And then I calculate my weighted average days, right? And I calculate my weighted average days for excellent accepted and then detailed review and accepted. Okay? All right. And so then, of course, the next one we want to look at is the rejected orders. So again, you parse out. We're only looking at the steps in the process that have the rejected orders, right? And one of the reasons you do this is if you're trying to make the most difference, right? If you're looking at your activities and trying to make the most difference, well, which one has the largest volume through it? You know, if you looked at this process and there was a way to make a difference in the initial reject, to take that down from 6 days to 5, that would have a larger impact of improvement on your process, right? So understanding where the variation is coming from is important when you're doing your analysis. So same point of view, though, we're taking how many days do we have in each category that we calculated earlier on, right? We have 75 applications going through the excellent but rejected, We have 225 going through the detailed review but rejected, and we have 500 that are going through the initial review and then are rejected outright. Okay, so we again calculate the weighted average and end up with our average flow time there of 11.34 days. Okay, so what did we learn from that? Again, I wanted to make sure that you're clear on the difference between linear and nonlinear. You're probably tired of hearing me say that, but I repeat it because I think sometimes you might not hear it the first time, so I want to make sure you have that opportunity. Okay? When using Little's Law, what can I do to determine flow time through the system in a linear process that I cannot do in a nonlinear process? So what can I do, Zach, what can I do in a linear process with flow time that I can't do in a nonlinear process?
Is it sum your
Right.
your inventory, or excuse me, your flow time?
Right. I can sum my flow time in a linear process, but I cannot do it in a nonlinear process. So, Spencer, how do I calculate flow time for the entire system in a nonlinear process then? What's the quickest way to do that?
You use Little's Law on the average for the systems.
There you go. I use Little's Law on the average for the system. If I want to look at different breakdowns of certain portions of the process, then I'm going to have to use the weighted average approach, right? But Little's Law for the entire system is 10 times quicker than trying to go through every step of doing the weighted average, okay? All right. Because we're a little short on time, I'm going to go ahead and not do, there is an example here. I'm not going to do that one. I'm going to go ahead and move on and do some nonlinear process practice problems that come from our textbook. Okay? And so, discard. Okay. All right, so the first problem asks us, there's a drive-through customer, this is problem 3.2 from the back of your text. At the drive-through counter of a fast food outlet, an average of 10 cars waits in line. Okay? The manager wants to determine if the length of the line is having any impact on potential sales. The study reveals that on average, 2 cars per minute try to enter the drive-through area, but 25% of the drivers of these cars are dismayed by the long lines and simply move on without placing orders. Assume that no car enters the line, leaves the line without service. On average, how long does a car spend in the drive-through line? Okay, so our question is, let's go ahead and let me show you the diagram of what that looks like. So we've got 2 cars per minute that are trying to enter. 25% are leaving without entering due to the line. Okay. And so if I'm going to draw my table, it's going to look like this. I need inventory, throughput, and flow time, right? And you can see that I almost always just put the formulas up here to keep me honest with what I'm doing in the table. Okay, so how many cars per minute are attempting to enter? We've got 2 cars per minute, right, that are attempting to enter. And how many of those actually get into the drive-through? How would I calculate that? So think of the blue boxes, they're in the drive-through, they're going through the drive-through process, right? 25% exit before I ever even get there. So how many are actually entering the drive-through process?
0.75.
Yep, so 2 cars times 0.75, right, gives me 1.5 cars are actually entering the process, okay? So if I have 1.5 cars entering the process, let me read you the problem again, and you tell me how many there are in inventory. At the drive-through counter of a fast food outlet, an average of 10 cars wait in line. Is that our inventory? An average of 10 cars wait in line. So that is our inventory, right? So if my question is, well, how long do they actually wait in line? I'm going to take my inventory, right, and divide it by my throughput of 1.5 cars per minute. So on average, they wait in line 6.7 minutes, okay? All right. So that was 3.2. Let's look at 3.4. Okay, give me just a second. And like magic, right, we have a diagram. Is this a linear or nonlinear process? Courtney, linear or nonlinear?
Linear?
Nope.
No, it's non-linear.
Nonlinear. Because if you look at the diagram, why we say that is because every throughput unit, we've got 55 per hour, you can see where they split off, where some of them go to the doctor and some of them go get a prescription. So therefore, it's nonlinear, okay? All right. So if I read 3.4, a hospital emergency room is currently organized so that all patients register through an initial check-in process. At his or her turn, each patient is seen by a doctor, right? So here they come in and they wait, right? And then they're seen by a doctor, and then exit the process either with a prescription or with admission to the hospital. So prescription or admission, okay? Currently 55 people per hour arrive at the ER, 10% who are admitted, right? So 10% in admissions, and 90% then are getting prescriptions, okay? On average, 7 people are waiting to be registered. So here's my buffer where we have 7 people waiting to be registered, and 34 are registered and waiting to see a doctor. So again, over here I have 34 people that are registered and waiting to see a doctor. The registration takes on average 2 minutes, so my flow time for that step is 2 minutes, okay? Among patients who receive prescriptions, average time spent with the doctor is 5 minutes. So the average time that I spend with a doctor to get a prescription is 5 minutes, okay? And among those admitted to the hospital, the average time that they spend with the doctor is 30 minutes, okay? So that's how long that step takes is 30 minutes, and this step takes 5 minutes, okay? So then our question is, on average, how long does a patient spend in the ER, okay? And so you can see I went ahead and set up the table, and the first thing I do is put all of the steps that we've identified in our diagram, right, into down the left-hand side of our table, because we need to know inventory, throughput, and flow time for buffer 1, that same information for registration, that same information for buffer 2, and that same information for doctor admin and doctor prescription, okay? So I think it's easiest to start with throughput when you're doing a problem like this, okay? So what's our throughput at buffer 1? Let's go with Taylor. What's our throughput at buffer 1?
55 people an hour.
Yep, it's 55 people an hour, okay? What about at registration, Rachel?
55.
55, right? Courtney, back to you. What about at buffer 2? How many people are going through that step of the process?
55.
55, that's right. Zach, how many are getting admitted to the doctor?
34.
Okay, there are 34 people waiting here, okay? But that's the inventory at that step. That's how many people are waiting. And then we take our snapshot of what's in there. So we've got these 55 people an hour that are flowing along this process. how many are how many are going into the doctor admissions process? Hunter?
5.5.
Right, there's 10% of those. So you're taking that 10% and you're applying it to the throughput. So you've got 5.5. Okay. Spencer, what about how many are going through the doctor prescript?
49.5.
Right, you can do that in two ways. You can take 55 minus 5.5 or 55 times 90%, right? All right, so now you've got your throughput for every step. And in almost every problem that you're going to do in this class, you're going to be given the throughput, right? So that's why I would always start there, because then you eliminate some other information. Okay, Andrew, I'd like to fill in my inventory that I know. What inventory do I know from this problem?
Buffer 1 has 7 people.
Mm-hmm. And what else?
Buffer 2 has 34.
Buffer 2 has 34. Okay, Emily, I'd like to fill in the activity times that I know. What do I know about activity times from this?
Well, there's 30 minutes and 5 minutes.
Okay, so I know that
2 minutes.
in admin I've got 30, and here I've got 5.
And
Okay.
then registration is 2.
Mm-hmm. Okay, so I think we've hit all of our activities then, right?
Mm-hmm.
And usually early on it's going to be just like this. Your activities, you're going to have flow times for, and your buffers, you're going to have inventory for, usually. Okay, so I've kind of filled out my table, so I've got 2 of 3 pieces of information, right? So now I can figure the third piece of information. I do want to make sure, okay, they're asking us, we're given time in minutes, and we're given throughput in people per hour. We have to make sure that they're in the same unit of measure. So it becomes 55 people per hour, and I can, the algebraic thing is times 1 hour for 60 minutes, which is the same as dividing by 60. Okay, so it's 0.9167. Okay. And then this is going to be equals 5.5, right, divided by 60, and equals 49.5 divided by 60. Okay, so now I have my throughput per minute across every step. Okay, so I can then, I usually start out with one column or the other and just consistently fill in the blanks, right? And so for registration, okay, Kaylin, how am I going to calculate inventory for registration?
You're going to do the R times the, you're going to do T, or 2, sorry.
Yep, nope, that's right. So that's exactly right. So it's inventory times throughput, right? And then I can do that same thing, right? So Taylor, we're back to you. For Dr. Admit, what's my inventory going to be?
It's 2.76.
Oh, did you calculate it already? Okay, so it's this times this, right? 2.75. Okay. And for Dr. Prescript, Rachel, what's my formula here?
0.825 times 5.
0.825 times 5. There we go. All right. So what I know then is I can look at this, and what can I do, Courtney? What things can I sum and what things can I not sum here? You remember when we...
With it being nonlinear, you can't sum your flow time, but you can the inventory.
I can sum my inventory, right? Mm-hmm. So there's my inventory. Zach, what's my throughput for the entire process?
Can you...
So I don't sum it. If you think about, if we put a box around this entire process, how many units are flowing through the entire process?
49.5.
That's what's coming out here, right? And 5.5 are coming out here. So a total of 55 are exiting too, right? So your throughput, you think about for the entire process, you think about how many are coming into and going out of for the entire process. And it's going to be 55, okay? All right, so that being the case, then I can calculate my average flow time, right, using Little's law. Okay, you know what, let's finish, I'm sorry, we should finish this, right? So I can finish the flow time in each step by taking inventory divided by throughput. And the beauty of doing it in Excel, of course, is you can just copy and paste the formulas. Okay? but I cannot sum that flow time, right? I can calculate it by taking inventory dividing by throughput, and it's 54.227. If I summed up across all the steps, right, that comes to 81.7. But not every flow unit goes through every step, so that's not a fair representation. So we'd say, on average, how many patients are being examined by doctors? Okay. What would I, if I wanted, so I've got the answer. Where does that come from? How many patients are being examined by doctors? Rachel?
It's the inventory, the admin, and the admission and...
Yep. I'm adding up the inventory at the admin, doctor admin, and doctor prescriptions stages. So that's how many are being seen by a doctor. On average, how long does a patient spend in the ER? Okay. Well, they spend 54.227. Okay. And again, I could have done it the weighted average way, which is what I'm showing you here, but really, how much quicker and easier is it to do what we just did with summing up the inventory and using the throughput?
Can you put this little Excel document on like Canvas or something so we can go back and reference it?
Yeah, I think it might be.
Integrity. Yeah, it should be on Integrity video, right?
Yeah, it'll be on the Integrity
I mean,
video,
like,
but usually
actually, like,
the actual Excel file, yeah, I will.
okay.
I will. I'll check and make sure it's not, because sometimes
Okay.
it is out there already. But so again, just kind of the differences, the tweaks between a linear and a nonlinear. They're not hard once you get it figured out, right? Does it seem relatively straightforward now that we've talked about linear versus nonlinear? And then it's a matter of understanding the problem and being able to diagram it, and then breaking it apart and filling in the table. And again, I almost always start with the throughput, and then just for consistency, because you have that information given to you in the problem, and then fill in the blanks in your table of where you've been given inventory and where you've been given flow time. And at the end of the day, if the problem's written right and if you've done your homework right, you're going to have 2 out of 3 pieces of information, and you're just solving for the last one. Okay? All right, so that was problem 3.4. We said we wanted to take a look at problem 3.5. Okay? Okay, so 3.5. One of the reasons that I started to write my own problems is because this textbook sometimes kind of goes from one problem to the next, and it wasn't clear to students that that's where the throughput for this problem comes from, is from the previous problem. So in 3.5, it says a triage system has been proposed for the ER described in 3.4, meaning that we have 55 per hour. Right, so you can see I've left that in the table as our throughput and calculated again our people per minute. Don't think we need to reinvent the wheel on that. Okay. Under the proposed triage plan, entering patients will be registered as before. So they come in, they register. They will then be quickly examined by a nurse practitioner who will classify them as simple prescriptions or potential admits. While simple prescriptions will move on to an area staffed for regular care, potential admits will be taken to the emergency area. Planners anticipate that the initial examination will take 3 minutes. Okay. They expect that on average 20 patients will be waiting to register. So we've got 20 patients waiting to register. We've got 5 will be waiting to be seen by the triage nurse. So there's 5. Okay. Recall that the registration takes an average of 2 minutes per patient, and the triage nurse is expected to take an average of 1 minute per patient. Okay. Planners expect the simple prescriptions area to have an average of 15 patients waiting. So here's our prescriptions with 15 people waiting. Okay. And as before, once a patient's turn comes, each will take 5 minutes of a doctor's time. Okay, so there's our 5 minutes. And the hospital anticipates that on average, the emergency area will only have 1 patient waiting. As before, once that patient's turn comes, it will take about 30 minutes. Okay. Assume that as before, 90% go through simple prescription, and assume the triage nurse is 100% accurate. And under the proposed plan, how long on average will a patient spend in the ER? Okay. So again, we've got our table set up, right, with all of the steps in the process listed on the left-hand side, and then we start filling in the blanks. Okay. I'm not sure where I'm at, but Spencer, I'm just going to pick on you.
Okay.
What do I know about inventory? So in the buffers, what inventory do I have?
You have 20 patients at buffer 1.
Mm-hmm.
5 at buffer 2.
Okay.
Is that 15 at 3? And 1 at buffer 4.
Okay, there we go. All right. Then with that being said, Andrew, what do I know about flow times?
You can't just add them up.
I can't just add them up, but what am I given in the problem?
You're giving the throughput and
So what flow times for each activity? That's what I'm looking for now.
okay, the flow times for each activity.
Mm-hmm.
You got 2 minutes at registration 2, and then 1 minute at the triage exam,
Great.
and then I can't read the other ones because I'm blind.
Okay, well, they're probably a little small, too. It says doctor prescription takes 5 minutes, okay? And it says that doctor admit takes 30 minutes, okay? All right, now again, we're just coming back and we're filling in the blank. Inventory is equal to throughput times flow time. Throughput times flow time. And so I'm just going to copy that formula, throughput times flow time, throughput times flow time, and throughput times flow time. And I can sum up and get my inventory across the entire system, and that's 50.625. We're just going to look at the table now so you can see that a little bit better. And then to calculate my flow time, it's going to be inventory divided by throughput. And so I'm just filling in the blanks in my table, inventory divided by throughput. Okay. And so now I've got flow time at every activity and buffer. I've got inventory at every activity and buffer. I know that on average there are 50.625 people in the system. There are 55 people per hour going through the system, and that leaves me with an average flow time of inventory divided by throughput of 55.227. So if I compare that to the last problem, right, where we were at 54.227, it's actually taking a little more time on average. Okay? All right, let's see what other questions they ask or answer then. So in 3.5 at the bottom they say, so we've answered on average how long will a patient spend in the ER, right? We've said 55.227 minutes, okay? On average, how long will a potential admit spend in the ER, okay? And so what I've done is I've highlighted the times that it takes for someone to go through that process, right? So if I'm going through the process to be admitted, that's the yellow. That's what we have highlighted here. They're not going through these steps. So then I can sum up those steps, and the doctor admit then is 71.2 minutes, right? It's the sum of those activities, okay? All right, so again, do you kind of see how you can get the average times by, if you're looking here, if I'm just interested in average flow time, come on, Arrow, come on back over. You can do it. There we go. I can take the time that it takes at each of these steps and say that's on for that particular process, right? And that's what we've done with this doctor admin stage. All right, so let's keep working here. And we want to look at problem 3.6. Okay, problem 3.6 says, we're going back to the same exercise. Once the triage system is put in place, it performs quite close to expectations. All data conform to planners' expectations except for one set, the classifications made by the nurse practitioner. assume that the triage nurse has been sending 91% of all patients to the simple prescription area, where in fact only 90% should have been so classified. So the remaining 1% is discovered when transferred to the emergency room by a doctor. Assume all other information from exercise 3.5 is valid. Okay, so basically what we're saying is that triage nurse makes a mistake with 1% of the patients that go through there. Okay, and so how that changes things is, I'm just going to show you how that changes the look of it. Right, we now have 91% going to this path originally, 9% going to this path originally, and then 1% getting up here in the prescriptions and then going, oops, wait a minute, you have to come back down through here. You have to come back down to the admit process. So you're just adjusting then, you have to adjust your throughput. Okay, so our throughput that's at 55 per hour, when it goes then from the triage to the doctor admit, then we have to take it times 91%. Okay, and then what about the throughput that comes through here? What are we taking it by? So it's 55 per hour times what?
10%?
It is 10%, okay? Because you have 9% coming in on this arrow and you have another 1% coming on this arrow, okay? So you have to use the throughput for this step off of however many arrows are coming into it. So all you're doing then is taking 55 times 10%, which is 5.5, and then recalculating. So that's the only change that we're seeing from 3.5 to 3.6. So we're saying basically we have some rework in the process, right? Where we have to go back through and take a look at that. Okay, let's see. That really, the next one I think is not value added. I think we've seen enough of the examples today that you're going to be able to get through that. And the reason I say that is it takes a little bit to explain the diagram, and by the time we explain the diagram, we're going to be out of time. So what I'm going to suggest is you'll have these for examples, right? And then you need to go out and work on the 3C homework, and they're going to be very similar to the types of problems that we saw here in class. And just keep linear versus nonlinear straight in your head, and you should be in good shape. Okay?
You said no class next week.
No class next Tuesday, but you do owe me, and I'll post a kind of where you can post a text about who's doing what when. And if you want to see me, I'll be up in my office for sure during class time, or schedule an appointment, and we'll go through it. All right? Other than that, I can't believe I'm saying have a good weekend. I can't believe it's that time already.
Time flies when you're having fun.
Planning on going home, but I think
Well, good luck.
I'm going to try and figure out this woman's name. I hope so.
Oh, yeah, your participation stuff? Okay.
I'm going to go try to take that one.
Okay, good.
Class, so,
Later on today?
yeah, 3, 4 o'clock again.
Thank you. Oh, I guess I could stop the recording, huh?